Welcome to our senior capstone presentation. My name is Nate Williams.
Jacob Tobias.
This is Nicola Rosso.
Jacob Dirks.
This is Wilson Wang.
And I'm Matt Prado.
For our project, we were tasked with redesigning a gooseneck style hinge intended for the door of a DC-9 aircraft. We were given a maximum volume that needed to stay within. Additionally, we needed to ensure that our design would be able to stay within allowable deflection limits under both compressive and tensile loading. Specifically, our hinge could deform by no more than 0.4 inches under a 6,000 pound tensile load or by 0.3 inches under a 3,000 pound compressive load. We were also required to develop a product that would not break under a one-time ultimate load of 9,000 pounds in tension and 4,500 pounds in compression. Lastly, in keeping with the guiding principles of aircraft design, we wanted to ensure that our part would be as light and as cost-effective as possible.
The design process began by using the geometry of the original envelope to determine stress demands around the hinge. Due to manufacturing costs and construction simplification, we settled on creating a hinge that was built of multiple sheets of steel 4130 with a uniform thickness all welded together. This thickness would be determined by analyzing stress demands around the hinge and choosing one that would keep demands below the yield and ultimate strength of 4130.
As we iterated through designs, we created them in SolidWorks to then be imported into Abacus, a finite element analysis software. Our results from Abacus closely matched our hand calculations at the same locations, which can be seen in the highlighted boxes. In the end, we designed and manufactured one aggressive and one conservative hinge. The conservative one being a solid piece throughout the whole part, while the aggressive one has overall less material and holes cut out in the web. The main component shared being an I-beam throughout its entirety because of its ability to resist bending about its strong axis.
Once our hinges were fully designed, we needed to create our pieces from the steel plate. Using a water jet at the UW Mechanical Engineering machine shop, we cut out our flanges and webs in order to reduce our costs. Next, at a local machine shop, the flanges were heated, bent, and welded together with the web and bolt holes.
Before testing could commence, we had to manufacture two fixtures that accommodate our hinge in the Instron testing machine. I manufactured these using a 2-foot-long block of 2024 aluminum on a 2-axis CNC mill. Here are hinges being tested in the Mechanical Engineering Building's Instron machine.
Upon testing, we found both hinges to undergo yielding much earlier than predicted by our theory. The initial response resembled FEA quite well, and you'll notice that elastic behavior continued as predicted. We would achieve acceptable deformation. However, we underestimated the extent to which the effects due to manufacturing would lower the strength of our material. Stress concentrations, residual stress, and heat-affected zones are present due to the annealing, bending, and welding of our part, all of which lowered the yield point of the hinge. In addition, due to the ductile behavior of steel 4130, we were unable to load the hinges up to ultimate tension before excessive deformation occurred.
Though our theory didn't match what we observed in testing under tension loading, we are very happy that we were able to create a product that was able to perform reasonably well within the confines of the assignment.
I'd like to give special thanks to Boeing's own Mitchell Malore and Matt Soha, as well as Professor Richard Weep for their help along the way. We'd also like to thank Bill Kuykendall and Miguel Gonzalez for their added assistance.